Hi, I'm Antonio Herrera, and today I'm going to explain what I did in my group of math with David in this video. In this project, we explored all three applications of math: a data modeling, isotope decay, and financial modeling. We use linear and exponential functions to analyze real-world situations.
So first we're gonna see the application number one, which is data modeling. We studied the percentage of people living in extreme poverty in Brazil over time, or X variable represents years after 2013, and our Y variable represents the percentage of poverty.
We created two models. The linear one was y equals negative 0.1698x plus 6.485, and the exponential was y equals 6.53 times 0.964 to the power of x.
Both show a decrease, but we choose the exponential model because the data does not decrease at a constant rate. So yeah.
At the beginning, poverty decreased faster, and then the rate slows down, forming a curve instead of following a straight line. This matches an exponential pattern, because also the exponential model has a slightly R2 value, meaning the data fits better. And also the rate of change is negative but not constant. It slows over time. And using this model, we predict poverty will continue decreasing but more slowly in the future.
So this is our work for application one. This is our graph, and
this is our table, which we saw which one was the exponential linear model, which fits better, and the exponential was the one who fitted better.
Okay, so this is application two, and we modeled the decay of carbon-14 using an exponential function.
In our initial model, the amount was 1,000, and the half-life was 5,730 years. So the equation is 1,000 times 1/2 to the power of x over 5,730. This is our final calculated model. Was approximately y equals 1,000 times 0.99987 to the power of x. In this model, A represents the initial amount and B represents the decay factor.
This is exponential decay because the amount decreases over time. At first, decreases quickly, but then slows down. The half-life means the amount is cut in half every 5,730 years.
This is useful in real life because carbon-14 is used to determine the age of fossils and ancient materials. So that was our day 2, and this is what we did on day 2. So yeah. Okay, so now we go to application 3, the financial modeling, and we analyzed how money grows using simple and compound interest in Guatemala, the United States, and Germany.
Simple interest grows at a constant rate because it is based only on the initial amount. Compound interest grows faster because it includes both the initial amount and the accumulated interest.
We found that Guatemala was the best option because it had the highest interest rate and monthly compounding. Compounding frequency is important because the more often interest is added, the faster the total grows.
We also saw that a higher interest rate alone does not guarantee the best outcome. Compounding plays a major role. Over time, compound interest grows much faster than simple interest, and the difference increases.
This is our day 3 modeling, financial modeling. Here we have Guatemala, United States, and Germany. We got the simple and compounding equation for all, and we saw Guatemala was the most accurate. So here we have all explanations, and yeah, Guatemala is the best option because it has the highest interest rate and compounds monthly. So it grows the fastest, and compound interest grows faster than simple interest because it earns interest on previous interest. So in conclusion,
all the application uses exponential models to describe real-world behavior. The data modeling exponential functions describe changing rates. In isotope decay, they show how quantities decrease over time. In finance, they explain how investments go through compounding.
A key takeaway is that exponential models are more realistic than linear ones in many real-life situations. One surprising insight was how powerful compounding is over time, and overall, this project showed how math can be used in real-world situations.